To understand a little more deeply what's going on with the transformation from r theta coordinates to xy coordinates or to xyz coordinates, let's start with the region of r versus theta that we considered earlier. 0 less than or equal to r less than or equal to a, 0 less than or equal to theta less than or equal to 2 pi. Now, if r and theta are interpreted as polar coordinates of a point in the xy plane, this is just a circle of radius a. It's a complete circle of radius a. However, in r theta space, or in the r versus theta plane, this can be represented as simply a rectangle. 0 less than or equal to r less than or equal to a, 0 less than or equal to theta less than or equal to 2 pi. If we graph r versus theta as opposed to graphing in the xy coordinate plane, where r and theta have common interpretation as the distance from the pole and the angle with respect to the polar axis, we're just going to do this in r theta space, where we have an r axis and a theta axis, so that r equals a corresponds to this, r equals a corresponds to this horizontal line, theta equal 2 pi corresponds to this horizontal line, and our inequality, 0 less than or equal to r less than or equal to a, means that r is between 0 and a, somewhere within this strip. 0 less than or equal to theta less than or equal to 2 pi simply means that theta occurs somewhere within this strip. A partition of the r interval gives us, let's say, a typical r subinterval with a sample point. We'll call it r sub j star. There's no reason that r has to come before theta. There's no reason that we can't use j for the subscript on r. From 0 to 2 pi theta, we partition that. We get a typical subinterval. Theta sub I star being a sample point in the interval. This interval is delta r. This interval is delta theta. That means the width of the interval here is delta r. Width of this interval is delta theta, so we have a region that's delta r here and delta theta here, with sample point theta sub I star r sub j star. Now, if x equals r cosine theta, y equals r sine theta, then we can map this r theta region into our x versus y, or y versus x coordinate system. There's no reason that this has to be the relationship between x, r theta, and y. This could be any relationship at all, but if we're going to let r and theta be the polar coordinates of a point, then this has to be the relationship. If that's the case, then delta r causes a displacement x sub r delta r plus y sub r, x delta r I plus y r delta r j equals xr plus yr, xr I plus yrj times delta r in the xy plane, so that if x of r sub j star theta I star and y of these coordinates yields this point here. So this is x of rj star theta I star y of rj star theta I star. I think I'm off camera here. Let's see if we can bring that back. Okay, if we've got that point down here, then that point corresponding to some point within this delta theta by delta r region of the r theta plane has one boundary that's equal to this vector, or approximately equal to this vector. So this is our vector x sub ri plus y sub rj, where x sub r and y sub r are the derivatives of the x and the y functions. And then that's multiplied by delta r, where again x, r, and y are evaluated at some point near this xy point, and they're rather these are evaluated at the rj star r theta I star coordinates. They originate at a point that corresponds to one of the corners of this region, not the sample point, not the mapping of the sample point, but the mapping of, let's say, the lower left-hand corner. Might be any corner, but for reference, let's pretend it's the lower left-hand corner. Now, we've seen this before, but we haven't related it to this kind of a depiction of the r theta region. Okay, so similarly, delta theta causes displacement x theta delta theta I plus y theta delta theta j, which is just x theta I plus y theta j times delta theta. And that displacement is off in some direction here. Now there is a specific direction, but I'm trying to be general here, so that this vector is x theta I plus y theta j delta theta. And these two vectors define a parallelogram in the xy plane. That parallelogram corresponds to what we would get if we mapped every point within this r theta region into the xy plane using this transformation. Another increment of this subdivision might be, well, let's say it might be adjacent. Let's say here's a second interval. Then this interval is going to be defined by another sample point. These vectors will be evaluated at that sample point, and they'll give you another region over here. Now this mapping is 1-to-1, and it has an inverse mapping, and you're familiar with this mapping and its inverse. The inverse mapping being the one that takes the xy coordinates and gives you the r theta coordinates. And the r coordinate is square root of x squared plus y squared. The theta coordinate is the arctangent of y over x plus pi if x happens to be negative. A mapping you should at this point be familiar with. In any case, we have this mapping here, and the point of mentioning this is 1-to-1 and it's 1-to-1 if we come this way is that every element of this region is going to map, if we map every element of this region onto the XY plane using this mapping, then the two regions are going to have one boundary in common. In general, for a general mapping, not necessarily this mapping, the boundary could be any of these regions. However, let's assume that the boundary is this region. Now, this region here, the first region, is only approximated by this parallelogram, and this region would be approximated by another parallelogram. There could be a tiny bit of overlap or a tiny bit of space left out between these two regions depending on the nature of the map. But if our delta R and delta theta are small enough, the proportional overlap or the proportional region missing from these two is going to be very tiny compared to the total area of the regions, and it's going to disappear as delta R and delta theta approach 0. Now, if we subdivide the entire region of definition, then we're going to get a bunch of regions over here. Okay, and we don't know for sure exactly what they look like. In the general case, though, we do know what they look like for this particular mapping.